Hello, my name is Arthur Molina, and today I will be talking about the RSA encryption scheme and its methods and processes. We'll begin with the brief history of the RSA encryption scheme. The RSA encryption scheme was invented by three people. Those three people are Ron Rivest, Adi Shamir, and Leonard Edelman, and they invented the RSA encryption scheme in 1977 while they were students at MIT. Continuing, we could also consider another contributor of the RSA encryption scheme, which is Clifford Cox. He came to a similar result in 1973 while working for the GCHQ. The only issue was that his work was considered classified at that time, and it wasn't until years later that it was released. Why are encryption schemes needed? So they're needed because they're useful to send confidential information. Also, they tend to be difficult to break, which is why they're used. And furthermore, they're efficient, meaning that the person using them has little to no trouble trying to implement them to the information that you're trying to send. What is the RSA encryption scheme? So the RSA encryption scheme relies on the use of primes, and its securities stems from the difficulty of being able to factor a product of primes. Also, we'll be going over the different mathematical methods that are used in the RSA encryption scheme, such as Fermat's-Little theorem and Euler's phi function. We'll begin with Fermat's-Little theorem. So if we consider p to be a prime and a to be any integer, then if we consider a to the power of p minus 1, and if we take the modular arithmetic with modulus p, we get 1 if p is not divisible by a, and we get 0 if p is divisible by a. We can then consider an example using Fermat's-Little theorem. So we let p equal 3, which is prime, and let a equal 10, and 3 and 10 are not divisible. So overall, we reach the result of 100 equivalent to 1 mod 3 using Fermat's-Little theorem. And for the final step, we have 100 minus 1 divided by 3, which is equivalent to 33. So we saw in the previous step that if p is any prime and a is an integer not divisible by p, then we get that p divides a to the power of p minus 1 minus 1. And overall, we really don't care about the final integer we get, and we don't care because we know we must get an integer as long as one of the criteria is satisfied. Next, we consider Euler's phi function. So if we take a prime m, then Euler's phi function is a function that yields the greatest common denominator of 1 if we take an a, such as the a satisfies the criteria of being greater than or equal to 0, but strictly less than m. So we could consider a prime number like 3, and we should get two results using modular arithmetic. So first we'll begin with 1, and then we'll multiply by m minus 1 integers, and we'll create a table, and we'll compute this using modular arithmetic with the modulus being m, and the result should be an m by m table with m minus 1 results. So as we see here, we let m equal 3, and using Euler's phi function, we get the following table, such as we multiply 1 by 1, which is then equivalent to 1 mod 3, and we multiply 1 by 2, we get that it's equivalent to 2 mod 3, and we get the same result for 2, such as we multiply 2 by 1 and 2 by 2, and we see that we only get 2 overall results, 1 and 2. So next, we consider important proposition regarding an RSA. So for the sake of time, we won't be going into too much detail. The reason we mention this proposition is because it provides the overall foundation for the RSA encryption, because it allows us to determine whether our chosen numbers are compatible. And if they are compatible, we are able to compute the decryption exponent, which is useful in decrypting the plain text that is sent from the other user. As we previously mentioned, it is used to check the compatibility of the chosen numbers, but also the proposition uses Fermat's-Little theorem and Euler's function. And it is an important piece of the encryption scheme. And for a more concise proof, you could look at the second reference on the references page and look on page 121. So we'll consider two parties that are using the RSA encryption scheme, Bob and Alice, And this is just a brief overview of what to expect in the following slides. So first, Bob chooses his prime numbers P and Q. He then chooses his encryption exponent E. He then publishes his N, which is just a product of P and Q, and his exponent E, which is available to the public. Next, Alice chooses her plaintext M, which is the information she wants Bob to be able to decrypt. So then Alice encrypts M into C and sends that C to Bob. Bob then computes D, which is his decryption exponent, to be able to decrypt Alice's C. And once he does that using the decryption exponent, he finally obtains Alice's M. So we'll begin with the RSA key creation. So Bob chooses two primes. In this case, he'll choose P equal to 5 and Q equal to 11. And then he computes the product, which is just N equal to 55, which is his N. So then Bob chooses in his encryption exponent E, which is equal to 3. And then using the proposition that was previously mentioned, he checks the compatibility and he computes E and the product of P minus 1 and Q minus 1, and he gets the GCD, which is then equal to 1. Next, we consider the encryption step. So Alice chooses her plaintext M, which is equal to 7, which is the information she wants Bob to decrypt. M must satisfy the condition such that it is 1. It is either greater than or equal to 1, but strictly less than N. So using Bob's public information, she computes her C, which is what she'll send to Bob. So she computes C, which is equivalent to 7 to the power of 3 mod 55, which is then equivalent to 13 mod 55. And she sends C equal to 13 to Bob. So Bob knows what P minus 1 and Q minus 1 are. Then he computes the product, which is just then equal to 40, which allows him to solve for the decryption exponent, which he then has to solve for 3 multiplied by D, equivalent to 1 mod 40. And he could do this by taking the inverse modulo. And by doing so, he acquires 27 mod 40, which is his decryption exponent. This then allows him to compute for M. So he then computes C to the power of D mod N, which is equivalent to 13 to the power of 27 mod 55, which finally is equivalent to 7 mod 55. And he then obtains Alice's M. So why is RSA secure? It's secure because overall it is difficult to solve for X only knowing N and E, which is Alice's plaintext M. There are various techniques to be able to factor N, but they're not overall efficient. And factoring becomes difficult when prime numbers are involved, just because the only factors of a prime number are 1 in itself. However, we can ask the question, is it possible to infiltrate RSA? And yes, it is possible. We can consider a third party named Eve. So Eve is actually able to infiltrate Alice and Bob's exchanges. The only issue is that she runs into the difficulty of not possessing the same information that Alice and Bob have. And we can consider this diagram, which is just the overall use of the RSA encryption scheme that we explained in the previous slides. However, now we have a third party Eve, which she could then infiltrate the information sent between Bob and Alice. So we can consider an infiltration method, and we'll be considering a hypothetical scenario. So let's consider that somehow Alice was able to obtain the product of P minus 1 Q minus 1, which is equal to 40, and she obtains M because that is available publicly. And she could actually use the quadratic formula to be able to compute for P and Q, which she'll have to solve the following quadratic equation, which is x to the power of 2 minus P plus Q multiplied by x plus N. So first, she has to compute P plus Q, such that P plus Q is equal to N plus 1 minus the product of P minus 1 Q minus 1, which is then equal to 16. So then she has the following quadratic formula, which is x to the power of 2 minus 16x plus 55, which she then is able to solve, and then she gets x is equal to 11 and x is equal to 5, which is then P is equal to 5 and Q is equal to 11, which are the prime numbers that Bob had chosen previously. So overall, RSA is really dependent on the use of primes. And as we saw that the numbers must be chosen carefully. And it remains secure because it is difficult to factor a product of primes. as especially if those primes are like 10 digits or more, which is usually the case when used in everyday applications. So finally, RSA has held its relevance over time. Also, it is important to several aspects of our lives, such as being able to send credit card information securely, or being able to read your emails without having to worry whether someone has access to those emails as well. And it is still used today. It is not used in the sense as the way we explained it previously, but it is used in different variations because, like anything, it needed to be improved to ensure that it remains secure. But overall, it hasn't been scrapped entirely. Thank you for watching and have a great day.